So we are now going to take a little digression from techniques that we have talked about so far, which is what is called supervised learning, right? Supervised learning just means that you give the machine learning model both the feature as well as the labels, okay? So you are essentially asking the machine learning model to learn the relationship between the features you give it and the labels that are resulting from those features, okay? This is what is called supervised learning. Now, unsupervised learning is completely different. Unsupervised learning, you do not actually have a target you are aiming for, right? There isn't a real target. So when you do unsupervised learning, what you're trying to do is actually to infer from the data itself what are the properties of the data. When we talk about the properties of the data, we usually mean what is its distribution, and what are some of the key directions with the highest variances and so on and so forth. Okay, so we are going to include dimensionality reduction techniques as under this umbrella of unsupervised learning. Okay. So this is basically a summary of what is the difference between supervised and unsupervised learning. So in supervised learning, you are essentially learning from both example inputs and outputs, okay? In unsupervised learning, you are only learning from inputs. There's no output, all right? You are not predicting anything, right? In supervised learning, you almost always have very clear metrics of success, right? There are loss functions that people have used over and over again for supervised learning problems, right? So things like the mean square error. So there's one kind of loss function. The maximum likelihood, that's another kind of loss function. The mean absolute error, another kind of loss function, right? In unsupervised learning, it may surprise you to know there's actually no rigorously defined metric of success, right? I can't actually say I want to find, it's very hard for me to define what is considered a good unsupervised learning model before I have done that unsupervised learning, okay? Also, supervised learning tend to be much more computationally efficient because the algorithms are usually fairly well defined. In some cases, you actually have an analytical relationship. So for example, linear regression to solve for the coefficients, we just need to invert matrices, okay? Otherwise, you also can use numerical optimization techniques. All those tends to be computationally efficient. Unsupervised learning tends to be computationally complex. Okay, so they are much more expensive to do, especially in some instances. Okay. All right. So let me start with the first kind of unsupervised learning, which we actually talk about a little bit in the linear methods section of our lecture. Right. Now, the first kind of unsupervised learning, which is also a dimensionality reduction technique, is what is called principal component analysis, right? So in a principal component analysis, what I'm saying is that, well, I have a data set that has dimension P. In other words, let's say I have P features, and using those P features, I'm going to construct, I have a data set or that matrix that has P columns and n rows, where n is the number of observations, right? What I want to know is what are the principal components that provide the best linear approximation to the data that actually has a lower dimensionality, okay? Now, what that simply means is that I'm going to, principal component analysis obviously can be done for any dimension smaller or equals to P, okay? So if let's say I have 10 features, I can take up to 10 principal components, right? So, and what this means is that the first principal component always has explained most of the variance in the data. The second principal component will explain the second most variation in the data. The third principal component will explain third most variation in the data, and so on and so forth, okay? Now, obviously, if you go all the way to P principal components, you essentially already completely reconstructed the data and you have essentially done nothing useful, okay? Now, so let's say I have observations x1 to xn. So basically in principal component analysis, I'm going to look for the rank Q linear model for representing this data. In other words, I'm going to only use Q components rather than P components to represent this set of data. And this Q linear model is given by f of lambda equals to mu plus VQ lambda, right? Basically what mu is basically a location vector, and this V of Q is a P by Q matrix, okay? And the Q vectors actually have to be orthogonal to each other, right? Lambda itself is essentially a set of parameters, and what you're trying to do is to solve for that set of parameters, right? Now, in order for us to define what is the best Q linear model, what we need to define is basically what is called the reconstruction error, right? Now, the reconstruction error is something, again, that you have seen before, right? It's essentially your mean square error, okay? You take each of your x vectors, you subtract out this prediction from this Q linear model, which is mu minus VQ lambda I. You take the square norm, and then you sum it for all your n observations. And essentially what you're trying to find is the location vector, the V of Q, and the lambda that actually minimizes this square norm error of your L2 norm of your reconstruction error. Okay? All right. Now, obviously, this is a non-trivial process, but there are algorithms that have already been written for you to do this. So if you go about minimizing the function with respect to mu and lambda, you find that essentially your mu is just equals to the mean of x, and your lambda is given by this expression over here. And you can plug this into your function, and essentially now you just need to solve for your V of Q, which is your matrix, okay? And this is usually solved by some numerical algorithm, okay? So to solve this, what you do is that you use what is called singular value decomposition. So those of you who have taken linear algebra before, you will know what this is. The singular value decomposition of X is basically defined as the n by p matrix of centered at xi that gives you, essentially you decompose your matrix X into a product of three matrices, okay? The matrix U, which is a n by p orthogonal matrix, the D matrix, which is a diagonal matrix with singular values, and those singular values have the property that each of those the first singular value is the largest one, then you have your second largest singular value, your third largest singular value, and so on and so forth, okay? And this V is basically a P by P orthogonal matrix, okay? With what is called the right singular vectors as your columns, okay? So the product of the first two are essentially what I call your principal components, okay? So that actually gives you your principal components, and essentially x times your first right singular vector essentially gives you the direction, which actually explains the highest amount of variance among all other linear combinations of features, okay? So in other words, this gives you essentially the linear combination of your feature vectors that explains most of the variance in your data, followed by x times v of 2, followed by x times v of 3, and so on and so forth, okay? Okay, now let's take a look at the data, okay? So we are going to go back to our first lecture where you remember we tried to simulate the bulk modulus of the material with respect to different feature vectors like the atomic radius and the melting point and boiling point of your materials, right? Of your elements. So if we plot that data and we take the feature vectors and we construct our PCA and principal component analysis, and we plot the first principal component on the x-axis and the second principal component on the y-axis, this is basically the plot that results, okay? And you'll notice that what I've done is I colored the data points by the actual bulk modulus values themselves, okay? And you'll see that, for example, PCA1 actually explains quite a bit of the variance in the data, right? While principal component 2 actually explains slightly less variance, right? And what you can then do is that instead of doing linear regression on your raw features, you can actually do linear regression on your your calculated values of your principal components, okay? So obviously you will always choose the first principal components, then you choose the second principal component because they are arranged in order of how much they explain the variability of the data, okay, of your feature set. So this is basically what you actually get if you do a multiple linear regression based on these principal components. And you do notice that, again, the performance in terms of R-square is significantly improved. If you do not remember, originally just a simple multiple linear regression based on your all your features, you basically just get an R-square of 0.2 something. Here, you actually get an R-square of up to 0.55, so much better R-squared, and also your mean square error is also significantly reduced compared to your simple linear regression, okay? So the PCA type of dimensionality reduction followed by linear regression is somewhat similar to your partial least squares method that we already covered in the previous lectures, okay? All right. So this is just a code example to show you how you go about doing PCA analysis in scikit-learn. To do scikit-learn, they actually have a package called decomposition, and in the decomposition package, you actually have your PCA class. Again, what you do is that you just fit the PCA to your feature vectors, right? So remember, this is unsupervised learning, so the fit method does not include your output, okay? So there's no target vector when you call fit for a unsupervised learning or dimensionality reduction technique. And what you want to do is that after you call fit, you want to transform it into the actual feature vectors in the principal directions. You will just call it, you call the transform method for x, and you actually get your new x, which is your new feature vectors based on the principal component analysis of your x, okay? You can actually print out the explain variance vectors as well. And then, of course, what you can do is that you can do linear regression based on your principal components, and you can always select how many principal components you want to use. In this case, I'm selecting my first two principal components, so 0 and 1, and nothing above that, okay? So here I'm using the standard scaler to scale my data first, and then I'm going to do my principal component analysis, okay? So so I use the question mark to figure out what sort of inputs do I need for my PCA class, all right? So this is the doc string. And you notice that there is actually only one component that is actually immediately important, right? You need to specify how many components you want to calculate your PCA for, all right? Typical values, people usually do not want to work with that many PCs or principal components. Typical values are 2 or 3, sometimes maybe a little bit more. The reason why you, by far the most common is actually 2 components is because 2 components is very easy to plot, right? You can actually plot principal component 1 on one axis and principal component 2 on the other axis. And then you can plot what is the distribution of your data relative to principal component 1 and principal component 2, okay? So very common value is 2 or 3, okay? And then you go about doing what I just talked about. You just do your fitting, and then you do the transformation. Now, once you do the transformation, you see that you can print out the explain variance, and this tells you, this actually sometimes actually gives you a clue of how many principal components you want to use, okay? So you will notice that principal component 1 already explains 2.48 of the variance, principal component 2 explains 1.66, and then it progressively decreases, right? And you will notice that you probably want to start at 1 or 2, or maybe up to 3. 4 and 5 probably is not that useful, right? You notice that the values of the explained variance actually significantly decreases. What this means is that principal component 4 and 5, it doesn't explain that much of the variability in your features, right? And it means that it's probably quite a useless data point to be given to your multiple linear regression model, okay? All right, so you can then regress against the PCs, and this is just a plotting of the data of the bulk modulus with respect to the principal components. The nice thing about this is that you immediately see that it does help. You notice that there's a lot of variability that are explained by your first two principal components alone. That means that using this as your multiple linear regression input is probably a good idea, okay? And this is the linear regression model based on the principal components. The values are slightly different, probably because of some fitting and random selection, and that's it. But otherwise, this is no different from what you have done before with your multiple linear regression, okay? There are extensions to PCA. So instead of doing just your principal vectors, we can also do what are called principal curves, right? So these are essentially just an extension that instead of using just a vector, you are going to use smooth 1D curve approximations to the data and to actually construct your principal components, right? And similarly, there's another concept called principal surfaces, which is just a higher dimensional representation for using a curved 2D manifold to represent your data, okay? So these are definitely much less commonly used, okay? So typically, people just do PCA, but for more sophisticated data sets, you may actually want to experiment with them. All right. Now, another form of unsupervised learning is something that is very commonly done in a lot of problems, both in science as well as in social applications, right? And that is called cluster analysis. Now, cluster analysis just means, well, if you look at, let's say, the data as plotted in terms of some coordinates, you want to cluster your data such that they form sensible clumps, right? So you want to essentially group your entire data set into subgroups that within the group, the pairwise differences tend to be smaller than the differences between groups, okay? So this is essentially called clustering. So it is exactly what you would imagine it to be. You are essentially just trying to cluster things together. And there are a number of algorithms that are used to do this. One are combinatorial algorithms, where you are just modeling the data with no underlying assumption of any probability model or distribution. So you are not making assumptions like, well, this data, I'm going to assume that it is some form of Gaussian distribution and then fitting it. So in combinatorial algorithms, you are not doing that at all, okay? Now in mixture modeling, that's the exact opposite. You will actually assume that the data actually forms some form of probability distribution, and you are going to assume that all the samples are identically and independently distributed from that data set, okay? And there are also what are called mode seekers, where essentially you are trying to seek the most common occurrence of data from the probability distribution function, okay? Now, let me start with the first type, which is the combinatorial algorithm. This is actually very easy to understand, okay? Now, the first type of clustering algorithm is what is called k-means, okay? It is one of the most popular iterative descent clustering methods, right? And the way that you do k-means is that you are going to assume that the Euclidean distance, which is just your square norm between the data points are going to be used as the dissimilarity measure, right? So intuitively that makes sense, right? So we are assuming that the square distance between two data points basically shows you how dissimilar the data is. So that if the data points are very far away from each other, then they are very dissimilar. They probably should be in different clusters. While if the data points are very close together, then they should be probably from, there's a higher chance that they are actually from the same cluster, right? So in classic k-means, you are measuring the distance of every single data point from the centroids of your clusters, okay? Now, you are, of course, k-means is not limited to just using the centroids. You can also use other forms of metrics, okay? So for example, distance metrics wise, you can, instead of just using your simple Euclidean distance, sometimes you might want to use a weighted Euclidean distance. Now, weighted Euclidean distance, for example, you can penalize data points that are further away much more. For example, that may be one way you want to do it, okay? Or you can also weight certain clusters more than the other, right? Now, there's also things like periodic boundary conditions. This is basically distance where this is commonly used when you model crystals, because in crystals you have periodic boundaries, and for that you actually need to take care of that distance metric based on the periodic boundaries, right? And instead of using centroids of clusters, you can also measure distance to one of the points. So instead of calculating the centroid, you will just take one of the points as essentially the representative point for that cluster. And this has the advantage that in case you actually have an outlier, you have outlier points, then your centroids do not get overly distorted, okay? So this is just a modification of this k-means algorithm, right? Now, k-means is so simple that I actually can describe the entire algorithm to you using just a series of steps. In fact, just when I was a grad student, scikit-learn was not that well developed, or rather I didn't know that k-means was already in scikit-learn. I actually implemented my own k-means algorithm, okay? So it's actually quite simple, right? So let's say you have this data set, right? This is my original data set, and you are trying to cluster this data into 3 clusters, right? So let's say I'm setting k equals to 3, right? So the way that the k-means algorithm works would be that you will first start with an initial set of k-means, okay, k-centroids, right? So the way that you will do this is that maybe you just randomly choose, I'm going to take a set of points, and I'm going to initialize this as my one centroid. I'm going to randomly choose another set of points, and I'm going to select this as my second, calculate the centroid of those points, and this is my second centroid, and this is my third centroid, right? So there are different ways of initializing that first set of centroids. One is called the 4G algorithm, the other one is called just random partition. Doesn't matter. What you would just do is that you basically just initialize the set of first 3 centroids, right? Now, what you would then do is that you're going to calculate the distance of every single point to each of the centroids, right? So I'm going to take this point, for example. I'm calculating the distance between this point and this point. I'm going to calculate the distance between this point and this centroid, and I'm going to calculate the distance between this point and this centroid, right? And obviously, if you take a look at this point, it is closest to the red centroid, right? So what this means is that I'm going to color this red, and this is basically one of my points. And similarly, I'm going to do it for all the other points, and I'm going to get basically this partition, right? So all the points that are closest to the red, the blue centroid will be colored blue, and all the points that are closest to the green centroid will be colored green, right? And what you would then do is that you're going to iterate, right? And what you're going to do now is that I'm going to take all my points within the red region, and I'm going to recalculate the centroid again. So by recalculating, I find that now my centroid has shifted to this position, okay? And if I take all the green points, I'm going to recalculate my centroid, and now my centroid has shifted to this position, and now my blue centroid has shifted to this position, right? And then what I'm going to do is that I'm going to repeat the process. I'm going to calculate the distances of every single point to every single new centroid again.
and then I will have a new partition, right? And then you just keep repeating that process until your partitions no longer change, okay? So now you will actually have your clustering done, right? So this is the final result, okay? You basically now have these three centroids, and this is the clustering of the points based on the k-means algorithm, okay? K-means is very often used for vector quantization, okay? What is vector quantization? Vector quantization just means that I have a data set that is a range of values, right? And I want to just basically split the data into different clusters. For example, let's say I have a data set of metals and insulators, or rather, let's say I have a set of data of hard materials, middle hardness materials, and soft materials, right? And I want to cluster all those materials into 3 different clusters based on that categorization. I can actually use k-means to basically do that binning of data points, okay? So that is one approach that you can use k-means for. You can also use it for essentially just clustering in an image, right? And in your lab number 2, you will actually be using k-means for both applications. You're going to use it for both vector quantization as well as clustering of an image, right? So determining, for example, whether in your SEM image where your nanoparticles are, right? So how do you actually use k-means or some other algorithm to do that clustering? Now, the challenge in k-means has always been that one very simple question, right? It is k-means. How do you know what k is? Should k be 3, 4, 5, 6, 1 million, 1,000? Who knows, right? How many clusters do I have in the data set? So sometimes k can be chosen based on goals, right? So for example, you may want to cluster the data set in a way that is based on what you have, right? So maybe you only have k instruments and you want to bin the data into k bins and use specific instruments for each of the bins, right? So that would be one way that you will have an idea of what k should be ahead of time. That you can also bin, for example, compounds into different chemical classes. Again, this you may already have predetermined what sort of chemical classes you want to define, and that can actually come from your intuition, okay? And there's also something called gap analysis. I'm not going to go through too much about it, but basically the way that you do gap analysis is that you are going to calculate what is the largest change in the in this variable in the gap based on adding every single additional cluster, right? And you are going to choose your value k based on the value of k that actually gives you that largest change in the gap, okay? And that's another way that you can sort of guess at what k is supposed to be, right? More often than not, you will just experiment with different k values, and then you sort of see what actually comes out and what makes the most sense for your data, right? Now, for the lab number 2, you are actually not going to be given a value of k, except in one instance. So you will have to figure out what a sensible value of k is, okay? Now, another way of doing clustering is what is called hierarchical clustering. Now, hierarchical clustering is very different from k-means. You don't actually need to specify what the number of clusters are. The way that hierarchical clustering works is that you just need some way of defining dissimilarity between materials or dissimilarity between data points, okay? So what it produces is what is called a hierarchical representation, in which basically the clusters that are closer together in each level of the hierarchy actually have distances which are smaller than clusters that are further away in the hierarchy, right? And you can actually determine at what level, and at each level you actually merge clusters from the lower levels, okay? Now, there are two ways in which you can construct a hierarchical clustering. One is called agglomerative, basically bottom-up merging. So what you do is that you take your entire data set and then you merge points that are close by together, and then you move up the next level, and then you group clusters that are closer by together, and so on and so forth. Okay. Or there is also the divisive way in which you actually start from assuming that the entire data set is just one cluster, and then you split the data set, and then you split each of the split clusters again, and until you basically get a top-down splitting, right? So the way that hierarchical clustering is represented is usually in what is called dendrogram. This is what it looks like, right? So this is actually a fairly recent work. I think it's in 2016 or something, where people were looking at lithium superionic conductors, and they were trying to see whether if we cluster all the materials that are lithium superionic conductors versus materials which are non-superionic conductors, based on some set of based on their feature set, do I get all the lithium superionic conductors clustered in the same region, right? So this is basically the dendrogram of all the lithium superionic conductors. You will see that they use a agglomerative hierarchical clustering method, and the compounds in red are basically your known lithium superionic conductors. The green ones, some of them are the green ones are actually known to be non-lithium superionic conductors. And what you will notice is that it does seem that the lithium superionic conductors tend to cluster together closely, right? And this is basically one of the first few times that unsupervised learning approach has been used to try to identify where is the feature space that will give you lithium superionic conductors, okay? And lithium superionic conductors are actually a highly important class of materials because people are looking for all solid-state batteries where you replace the liquid electrolytes with a solid electrolyte, and lithium superionic conductors are what you use for that solid electrolyte in those all solid-state batteries. Okay. Okay. Finally, another way of doing clustering is using what is called density-based clustering. The most popular variant is what is called density-based spatial clustering of applications with noise, or DBSCAN, right? So the way that DBSCAN works is that it groups points that are closely packed together and marks points that lie alone in low-density regions as outliers. So in this way, it is actually somewhat more sophisticated than your k-means algorithm, okay? In your k-means, every single point is going to be allocated to one cluster, okay? In DBSCAN, essentially they look for clusters where there are very high densities and then, or high density of points, and any points that sit very far away from any of the centers, we are basically going to consider them as outliers. I'm not going to let them affect my clustering, okay? In DBSCAN, there are actually a few parameters that you will need to tune to basically to look at the results. Okay, so one is called the EPS, which is basically a measure of the what you're setting for the max distance between two samples for them to be considered in the neighborhood for the other, right? So you can imagine if your EPS is very large, then what will happen is that you end up with very large clusters, and if your EPS is very small, you end up with very small clusters and a lot more outliers, okay? You also have what is called min samples, which defines what's the minimum number of samples in the neighborhood for a point to be considered what is called a core point. In other words, what defines a cluster, okay? So again, if this number is too big, then you will actually have very few clusters, and if this number is too small, you will have too many clusters, okay? All right. So let me actually show you how this works for this clustering and analysis. What I've done is that I have basically created a distribution made up of three sets of Gaussians, okay? So look at this, right? So this is an artificial data set. So in lab number 2, you will be actually working with an actual experimentally measured data set, right? So here I'm just demonstrating how this works with an artificial data set, right? So what I've done is that basically I have randomly chosen 3 centers, and then I sample a series of points that are taken from a Gaussian distribution of the data points, okay? And of course, this is a 2-dimensional set of coordinates, so just x and y, okay? And then I'm going to apply my various algorithms to see what they give me, right? So for this is to actually run a k-means clustering. You import the k-means class from sklearn cluster, and it's quite simple. You give it the value of k, okay? So that's the one input you need for a k-means algorithm, and then you feed it to the data, and then you can predict the actual clustering, and then you can plot out the clustering using this code over here, right? And what you see here is that, well, depending on your value of k, the algorithm will say, well, if k is equals to 2, then all these things should be in one cluster, and this set of data will be in another cluster. K equals 3, this is precisely what it should have been, because my artificial data set was constructed from 3 Gaussians. So you will see that the k-means algorithm actually gave me a pretty good reproduction of what my 3 clusters are. And then, of course, because in real life, you don't actually know what your k is, so you will actually have to play around with it. This is k equals 4 and k equals 5, and essentially what the algorithm does is that it increases the number of clusters, and then you classify things into more and more clusters. Okay?
Excuse me.
Yep.
So, like, can there be a matrix that can say that this much, like the value of k equals to this is the most optimal?
Sorry?
Like, can there be a matrix which can say that the value of k is the optimal value?
Yes. So that's where something like gap analysis will come in. You will actually analyze the the contribution of each additional cluster to the distance, the average distance between clustering points. Okay? And what you will do is that you choose the value of k that actually maximizes that quantity. Okay? That's why it's called gap analysis. I didn't want to go through it, but you can use that to sort of at least get some guess at what the optimal value of k is, but it's not a rigorous definition, right? You don't actually, nothing actually tells you what the value of k is, right? That's the thing about unsupervised learning. There's no one right answer. Okay? All right. This is DBSCAN. DBSCAN is basically also imported from the same package, okay, scikit-learn.cluster. And just to show you, this is the key parameter that I'm tuning here is what's called the EPS, which determines what's the maximum distance for something to be considered a cluster. And you see when your EPS is too small, okay, basically what happens is that everything is in just one gigantic cluster, right? And as you increase your EPS, you will get clusters forming. And what you'll notice is that DBSCAN actually is based on density, right? So what will happen is that your clusters will be formed in the areas where you have the highest density of points, right? So it is not going to form a cluster, say, somewhere here where there's only one point, but rather it will form in an area where there is actually a very great density of points, right? And you can just keep playing around with the EPS parameter, and then depending on how you cluster it, they either form things like 2 clusters or these 3 clusters over here. And again, like I said, there's no right answer. And every data point that is just outside, all those are considered outliers and they don't affect your clustering, okay? So, let me see. Yeah, this is just another data set, okay? So this data set, I deliberately made it such that the centers of the Gaussians are much further away, okay? So, and with this, we obviously can already see 3 clusters just with our eyeballs. and you can see that the DBSCAN actually does it pretty well. They actually cluster all that huge density of points over here, huge density of points over here, huge density of points over here. And then when you change the value of EPS, basically it only affects how many outliers there are. Because as you increase your EPS, essentially you are increasing the maximum allowable distance for something to be considered within a cluster, right? So, and that has the result of adding more points to your clusters. Okay. Now, if you look at this, so this is actually an example where I show you how you can actually use the matplotlib image class package to actually read in an image. You will need this for your lab number 2, because in lab number 2 I'm going to give you a image, okay, and that image is going to have values, and you need to use this method to read in the values, and then you're going to do your quantization as well as your clustering based on that image. Okay, so this is the command for you. This is the method for you to read in the image. Okay, and this just shows you the very simple examples of how you run a k-means clustering as well as a DBSCAN clustering on that image. Okay, so that's pretty much it for clustering.